Hello, welcome to episode 3 of our podcast, Innovating the Industrial World. I'm your host, John King, and I'm here with my good friends, Jim Hewston and Jeremy Larson. Why don't you go ahead and introduce yourselves?
Yeah, I'm Jeremy Larson, Service Director of the PMG Group, and been working with the company in calibration for just around 20 years.
My name is Jim Hewston. I'm the Director of Quality and Training for Cross. I've been with the company about 16 years now.
So today we're going to really geek out on metrology. This is going to be a lot of fun. This is the world I kind of grew up in. So who would have guessed, the name of our podcast is Innovating the Industrial World. Who would have guessed that just as recently as 2019, there was innovation in the metrology world in a hunk of metal? So let's talk a little bit about what happened in 2019.
So actually, it's pretty interesting. The kilogram actually has been around since about 1879. They actually casted it and created a hunk of metal that was a little bit bigger than a golf ball.
So when you say the kilogram, you mean the kilogram?
Yeah, absolutely. The one that's actually in France, or just outside Paris, at the International Bureau of Standards. And what's interesting about that one was everything is compared back to it. So
they call it the Le Grande. I'll work on my French accent. Le Grande K. The kilogram. Yep. It's under lots and lots of glass, and then what's it made out of?
It's made out of 90% platinum and 10%
iridium, I think. Yeah, I think that's right. It's intended to be an incredibly stable material to not change, right? So it is the kilogram in the entire world.
Absolutely.
So what happened in 2019?
So in 2019, we changed that standard from the known kilogram into a natural constants, so that we can actually recreate what a kilogram is in all areas of the world. So prior to that, we actually had to go and compare back to our national standards back to the Grande kilogram. And so now it's taking Planck's constants, the speed of light, and the cesium atom, and actually utilizing those natural phenomena and allowing us to be able to create the kilogram here in the United States. So
this idea of natural phenomenon or natural constants being used for standards is something kind of interesting, Jim. So there's a pretty good example of that everybody can really relate to.
Yeah, with the ice water there, one of the properties of water is that in a state of transition, the temperature will remain constant. So in this particular case here, we've got a glass that's got ice and it's got water in it. So as that ice is melting into water, it's transitioning. So it is at the freezing point and will remain at the freezing point, whether it's in the liquid or ice state, as long as there is ice and water in that solution.
Which is kind of cool. I mean, that's kind of interesting to think about. So like literally everybody in your kitchen, you can get ice and water and mix them together. And in a state, we call it a state of equilibrium. If you're constantly mixing it up and keeping that ice and that water going together, it's going to be exactly 0 degrees Celsius, 32 degrees Fahrenheit, right?
Yes. I
mean, exactly. So that's a really kind of a neat thing. That means we can repeat that anywhere in the world. Now, I will say this, something kind of it's important to know for those of you who know a lot about metrology is that's at atmospheric pressure. So we have to be really careful to think about what does the pressure here might be a little different than the pressure there. But it's important to know that, it's kind of an interesting thing to think. In our kitchen, we can have a primary standard that is no better or no worse than anything else in the entire world.
Based on a naturally occurring property.
Yeah. So I don't know if you guys can see this or not, but we have a glass of ice water on the table, and we've kept it kind of mixed up with a temperature probe in here. So what's that?
It's just below, right at 32 degrees.
That's awesome. Pretty cool, huh?
Yeah.
Okay, so back in 2019, as recently as 2019, so there was the kilogram. When did you say it was created?
1879.
So from 1879 until just 2019, there was a single kilogram. So one of the things that we do all the time, right, is we're calibrating weights and calibrating scales and making sure that people are measuring those accurately. So why is it important to have an accurate standard.
In the case of mass, commerce actually ties in. When the good old days when you would show up with a bushel of tomatoes and trade it for a flat of eggs, it didn't matter. But once you start bringing money into the equation, things like gold, then it's important because then you need to measure it, and we need to agree what that measure is. And if we can't agree on that measure, we can't do business to begin with.
Yeah, and this dates back to, I'm talking, we found evidence back to 3000 BC where it was, there were governments and nationalities that started creating standards to be able to measure what those things are and to be able to have something that they could really agree on. Because like you mentioned that in terms of commerce and that kind of thing, I mean, just think about that for a second. The United States, a lot of people remember, was on the gold standard at one time in 1933. So as recently as 1933, every dollar in existence was tied back to a certain amount of gold, right? And so that would say, okay, it's important for us to know how much that is because it literally mass governed how much gold there was.
Yep. It's even one of the phrases that shows up in the Bible and in church on occasional Sunday is fixing scales.
Yeah.
So at the end of the day, calibration is doing the Lord's work, right?
We like to think so sometimes, that's for sure. So one thing that people joke a lot about is the sort of 6 degrees of separation, right? That nobody's separated by more than 6 degrees or whatever. So when you think about how we calibrate a scale and how we make sure something's right, one of the things we have is one of our working standards. An example of a kilogram, Jim, you might want to show everybody.
That's it right there.
That's made of stainless steel, right? And it weighs exactly a kilogram. Kind of interesting to think about to what accuracy that particular standard is. But you see the one that's next to it, the shiny one? Yeah. Jim's pointing to that. For those of you who are just listening and not looking at it, Jim's pointing at it because you can't touch it. Why can't you touch it?
That is one of our Class 1 weights. The tolerances on those are such that if I were to pick that up with my bare hands, take it back into our lab to have it calibrated, the before and after I touched it, we would be able to measure basically the oil that transferred from my hand to that standard weight.
Which happens with artifacts. So we can use that shiny one, right, the Class 1, the Class S weight, to check the stainless steel one, which is what we check some of our working scales with. We don't check the really, really high-end balances of our customers, right? Okay, so let's think about how many. We talk about the 6 degrees of 6 degrees of separation, or the 6 degrees of Kevin Bacon. We'll play that game. Let's say how many degrees of separation is that stainless steel weight from the Grande K in France?
Well, off the top of my head, we send our standards off to a vendor.
Okay.
They in their lab have working standards that they would calibrate ours against.
Okay, so ours go to our vendor.
Yes.
So that's 1 degree to their working standard.
Yes.
Then what's next?
So their working standards, they would compare against their gold standard for their lab.
Okay, so they have a working to a primary. That's another layer.
Yep.
Okay.
Their primary, then we get sent off to a national standard. In this case, the United States, that would be NIST.
That'd be NIST in Gaithersburg, Maryland.
Yeah. So NIST would calibrate it against their working standard.
Oh, that's another layer. So that's 4 so far.
So
they have a working standard there.
Yes.
Yeah.
Now NIST, of course, compares all of their working standards against their primary standard.
So there is one Mac Daddy kilogram.
Yes.
in Gaithersburg, Maryland.
Yes.
Their primary
Historically,
standard.
Now this is the change that has happened. Historically, that primary standard would have been sent off to France, I believe, every 40 years for comparison against the working standards in Paris.
We're at 6 now, so we've already reached our 6 degrees of separation. But now we're at the working standards in Paris.
Yes. And then those working standards would get compared to the Mac Daddy kilogram
Grande K.
Yes.
And that's when we're talking about our primary standards. So we actually have a couple of layers within us, right? So we have our ultra class, we call them.
Yes.
And then we go to the shiny one, the Class 1. And then we go to our Class F, the working weights.
Yes.
That we would take out to see a customer. So you're talking about 8 or 9 degrees of separation between us, and which is kind of cool to think about. Like if I go out I'm working in in a factory, whatever, I got a scale, and anybody's coming to calibrate that, I know that there's only 9 different comparisons to get to the ultimate kilogram in the world.
Yes. Yep.
That's kind of cool to think about.
Yeah, and not something a lot of people know or appreciate or think about because it just works.
But what happens when they compare those?
When they compare them, I'm not sure what you're asking.
Well, when they're every time one of those layers, one of those degrees of separation occurs, there is errors introduced. Okay. I mean, you can only measure it so well, right?
Yeah. Okay. So I understand what you're saying there. So every link in the chain, every time that a standard is compared to a standard, that process has inherent errors in it. There are tolerances in the standard that you're comparing to. There's uncertainties associated with those measurements. So every time you add a link in the chain compared to Grande K, that error gets larger and larger and larger. Now, it may not be significant compared to what you and I are trying to do with the kilogram on our end of the business, but it's there.
And then some folks are doing some things that are pretty significant, right? So how accurately or with what resolution are our customers measuring things? I mean, I know there's lab balances that are doing what?
There's lab balances that'll go out, 2 and 3 places on a milligram. So, a milligram, kind of a quick, easy way to put that in your mind. A small paperclip is about the weight of a gram.
Yeah.
And a milligram, if you were to cut that small paperclip into 1 million pieces, that's the level at which we can make measurements here in our lab.
Yeah.
So we are by no means a national standard.
Yeah. So we're hearing people. Yeah, we know a lot of companies, especially in the pharmaceutical world. There's also, and certainly other industries, but when you're doing research and development and that kind of thing, people are measuring all the time to 1/1,000,000th of a gram, which would be, and a gram is 1,000th of a kilogram. Mm-hmm. So you're talking about of that Grande K. We have people that are doing work that need to be able to measure accurately in all kinds of different environments down to 1,000th of a millionth, which is pretty tight.
Oh yeah.
And so now you can start to see what happens in those 9 degrees of separation, right? So when we have an artifact, we're having to introduce those errors. We're not having to, but every time we compare an artifact, and how do we do that? We do that on literally, we used to do that on a mass comparator, which uses magnetism now, but in the past it used to just use levers, actually, right?
Yes.
It used to be an equal arm balance. One thing that we actually have one that's kind of interesting. We have the equal arm balance that the state of North Carolina used to use for their primary standards for 25 kgs and 50-pound weights. That's how scale companies would take their weights to the state and put them on that equal arm balance with that working standard.
When you talk about the error that's associated with those measurements, it's one of the things we do as part of our business is we always look for vendors that have smaller reported error because we want the best measurements in our process.
Yeah. Another error is, we go back to the kilogram, but we don't just use the kilogram to calibrate scales, right? So we have to drop down to different sizes of weights outside of that kilogram. And as we go and break from that kilogram down to the other ones, we introduce error all the way down. So we may have a milligram weight, but the problem is we had an uncertainty that was added at each one of those calibration steps to get down to that level also. So that also introduced a lot of error for the pharmaceutical world in today's time. So
what's kind of cool is that now that we've changed to this natural phenomena for mass, the primary standard in Gaithersburg, Maryland, what kind of so when you think about that sort of equal, there's an analogy to that equal arm balance, right? So instead of their primary and working standard that goes back to France, what's on the other side of that?
There's actually the kilograms on one side, and on the other side, there's actually a magnetic ring that they put different voltages in amps, and it actually creates a magnetic field. So it's creating the opposing force of what the kilogram should be. Over the time that they were actually going through and figuring out whether this would actually work, they actually had all that data from everybody calibrating, every 40 years, and they were able to find out roughly what that true value of a kilogram was.
And it's based on a natural phenomenon. So now it's like the ice water, right? So it's like the primary standard is repeatable anywhere in the world, and you don't have to send it back to France. So now we're going from 9 degrees to how many degrees of separation?
Well, theoretically, that cuts out France. That cuts out their working standard. That brings us back to a national standard.
Yeah. So we're talking about going from 9 to like 3 or 4.
Yes. Yeah. And where that could have been just the kg in the past, now they have the ability to determine other masses as well.
Yep. And in the it's something you'll hear us say all the time: nothing's impossible, just some things are more expensive than others, right? So that means now people can duplicate that. So you'll say you're a pharmaceutical company or whatever, you could have a primary standard in your lab if you wanted to.
Yeah. Furthermore, you could replicate that on the moon. You could replicate that on Mars. You could replicate that anywhere in the universe.
That's awesome. Are there other artifacts? So one of the things that we have here is a gauge block. This is obviously an artifact for a foot. So this is 12 inches, right? Mm-hmm. So at the same, did we do something along this lines in terms of changing that to a natural phenomenon?
We do. The artifact for a meter used to be in France as well. That has long since been replaced by the wavelength of cesium, I believe it is, in a vacuum. So now instead of there being an artifact somewhere in France that we all tie back to, now there's something that can be recreated anywhere because it's a natural phenomenon.
Yep, I think it's the speed of light or speed of cesium you mentioned before. It travels in a second in a vacuum. Mm-hmm. That's not easily, but it's measured. Easy is a relative term, but it goes back to anything's possible. Just
yeah,
that's right. But it's possible to be repeatably measured with lasers and that kind of thing. So what's interesting is that, I think it's interesting, that the technologies that we're using in the metrology world are getting more and more and more and more accurate. And so we're having to go away these artifacts. Now we're able to see how that's been changing, because this platinum iridium was changing over time, right? So how does that happen? How does it change over time? I mean, we've talked about it literally can absorb air molecules, things actually decay.
Yeah, I mean, the environment you're in is going to change something. I mean, we said day in and day out. And I think another thing is, as we've gotten better and better in the metrology world of measuring things, we've figured out the amount of drift that things actually occur. So as we were able to read further and further out past the decimal, we can see more and more drift. I mean, I remember, explaining on the length side, a millionth of an inch. I mean, you take a hair and divide it by 3 and then divide that by 1,000. That's what you're working with. And so just the air molecules and the different types of things in the air can affect that reading. So that's why those clean rooms are so important.
Yeah. What I used to talk to people about all the time is that the only way to measure that thing is you got to touch it. And if you're going to touch it, it's going to be affected by that. By whatever's touching it. We actually touch it. I think it's with like ruby tipped probes and that kind of thing.
Yeah, I've always been told once you get out past, a millionth of an inch, a lot of what we think of as metal being solid is very liquid and molecules moving around. And so moving to, the actual laser or the speed of light in the actual chamber allows you not to have any of those aspects involved. So it brings you back to something that's consistent and solid.
So we can take that 12-inch gauge block and we can use that to certainly calibrate or know if a tape measure is right or even if a micrometer caliper is right. But if you start going into getting even more accurate than that, which our people need to all the time. If you're building jet engines and that kind of jazz, you need to know exactly what the spec is. And so when you're doing that, typically you're going to want to use a laser. So one of the things that matters tremendously with materials like that is temperature, right? Yeah. So we have to do that in a 68 degree lab, exactly 68 degrees, so that we can have that repeatable temperature.
Yes.
Because we're still comparing those to artifacts, right?
Yes.
In terms of what most folks are working to. But then that next degree of separation will typically go to that constant. And so we kind of get back to our ice water, right? So we're trying to get to the point where almost everything that we're measuring, temperature, pressure, mass, torque, everything, it relates back to something that we can repeat almost anywhere.
The other thing too is a lot of the measurements in the direction they're headed. You talk about lasers and measuring electrical, whether it's current or voltage. We have the ability to measure that stuff in greater number of divisions than some of the methods that we've done it in the past. So if you're using a tape measure versus a laser, there's obviously a very different level of precision there.
There is, and that it's actually an interesting term about precision. So we talk, there's something about accuracy and resolution. So we can measure, you guys could teach a class on that. I mean, we talked about that lab balance. It measures things to a millionth of a gram, which is a thousandth of a millionth of a kilogram. That's the resolution, but the accuracy might be a little different, right?
Yeah.
Yeah.
For sure.
So sometimes you can measure out to the decimal places, but if it's not repeatable, if it's not in an environment that's repeatable, temperature, pressure, and all those kind of things, then it's not going to be as accurate, but it maybe have the great resolution.
Yeah, absolutely. We have a lot of customers that'll throw balances into areas where they shouldn't be using them, for lack of better. In the last couple digits of that balance will dance around. So they've got the repeatability, the resolution there, but they don't have the repeatability, so they don't have the accuracy that they think they do in those situations.
Yeah, a lot of your digital mics and things like that are the same way. They'll read out to 50 millionths of an inch or 100 millionths. The accuracy is actually about 1 or 2 divisions better than that. So a lot of people are asking, well, it reads this far, but how do we take care of this? And you explain to them that just because it reads that well doesn't mean it's consistently performing at that level. So, and another thing on the gauge blocks, a lot of our larger our national labs are actually using laser interferometry now to verify those. So it takes out a lot of the probing and things like that. So there's a lot of things that continue going back to these newer recognized standards.
Yeah. So kind of back to what changed in 2019, we're now literally they call it SI, but all of the standards are now based on natural phenomena, right?
Yes.
There's no more artifacts. I mean, we use artifacts, but that in terms of the primary standard is back to a natural phenomenon now.
Yes.
The unit as it's defined.
Yep.
That's awesome. So in terms of the degrees of separation, you can go back to Gaithersburg, Maryland, and the NIST. NIST is remind me of that again?
The National Institute of Standards and Technology.
Yeah. Go to NIST.gov, and you can look at all kinds of stuff in terms of the history and where that comes from and that kind of jazz. But that's also where you can get primary standards, and you can get also they have something called reference materials and things like that, right? So tell me a little bit about that. Why would you have a reference material?
Reference materials are more used in places where you're not making a measurement, but the properties are important to you. So let's say cement's classified, right? So how do we agree as to the material that I'm producing is of the grade that we've all defined and agreed to? Well, there may not be a measurement that we can use, but there's a reference material, so that we can see how the reference material versus my material and measure some properties based on that.
Yeah, and you can get things like gas detection systems, or you can buy a standard gas that is a specific defined standard, so you can use that to calibrate your measurements.
Yeah,
too.
we also use and used for quite a while is the actual hardness testers, the material blocks to verify the different types of hardness that are out there that we need to verify on when we're machining different types of equipment. So your B scales and C scales, things like that.
And you can order those materials from NIST. That's kind of cool. Pretty awesome stuff. I mean, it's pretty amazing to think that platinum and iridium, that's not supposed to change, changed a lot in 2019, right?
Absolutely.
Yeah. All right. Well, that concludes episode 3 of Innovating the Industrial World. We're kind of geeking out on metrology, and thanks so much for tuning in. If you'd like some more information, go over to www.crossco.com. If you like what you've heard, then click the like button or the subscribe button so that you know when we're going to do our next episode. And if you have any comments or questions, certainly put them in the comment section below, and we'll respond to those as quick as we can. Thanks so much, and appreciate y'all's help and time, and we'll talk to y'all next time.